Good afternoon, everybody. My name is Omid. I'm responsible for R&D activities at DEPsys. To start my discussion, this presentation, most probably you know that the electrical grid will be an important part of the future of the energy. And probably we are not all electrical power network expert, or we have not worked in the electrical utilities. So I take the opportunity to start by explaining how the electrical networks works. So the electrical networks are built to transfer the energy from the roots of the tree through this stable and strong trunk, and which is similar to the transmission grid with a lot of supervisory and control technologies. Then it will be distributed through lots of branches, which are distribution grids, which is almost not monitored, or very limited information about how the energy flows there. And then the energy will be finally delivered to the leaves, which are or households and smart meters, or where the energy will be consumed. So the purpose of my talk and the focus of my talk is only about the branches and this electrical distribution grids. There are new trends in terms of how these branches are going to be used in the future. The first trend is the electrification of heating and cooling consumption, and also the transportation. So this will be an increase of pressure on the electrical network. If you look at the distribution, a branch, so this is the current situation of the branch. It stands like that. We add some electrical vehicle on top of it. So the branch gets more pressure, it goes down. We put a little bit more of EV, so it goes even more down, and we see that there is a problem in the quality of the supply. And then if you even put more of electrical vehicle on this branch, it will break down. So it will not sustain as much as we want. The same story applies to the second trend, which is growth in the distributed generations, like PVs. When we add more and more, it goes up and up, more and more pressure, and finally will break down. So it's very important that in all the things that we're doing for the distribution grid, to think about the physical limits of this grid, and whether it can manage or can sustain it or not. So what is the situation of the grid? The distribution grid right now is geographically distributed everywhere. It's present everywhere. And the flow of energy in the distribution grid is based on the physical laws. It's not like human laws that we can change one time. So there are physical laws that we have to respect. And there's almost no monitoring. It's kind of black, these branches. And there's, of course, these new trends of utilization of the grid. So, of course, the electrical utilities are completely aware of this situation. That's why they're also looking at the new monitoring or control technologies that can be applied into the grid and help them to improve the operation of the grid. So, what we did in DEPsys over the past 8 years is to build a combined hardware and software technology. It's called GridEye. So the primary things that it does, it puts lights on the grid by doing a monitoring. So we get the monitoring information from the grid. We get the visibility. So this information about the visibility as a next step should be used for the status for getting information about the status and the health situation of the grid. And afterwards, as a unique feature that we have, we say that we are able to estimate some of the characteristics and behaviors of this distribution grid without knowing what is the size of the branch, what is the length of the branch, what is the diameter of the branch. Just by taking and collecting this measurement data, we're able to extract some important information from the electrical grid. So why do we really need it? What is the issue of existing grid analysis methods that we say, let's keep that one aside and go to this new suggested data-driven approach? So the existing way the usual way of grid analysis is based on two factors. There are two important points that are needed. One is the measurement, and the other one is the grid model. So usually when we go to the distribution grid, the grid model, in every case, grid model includes the grid topology, which is the connection between nodes, node 1 to node 2 to node 3, and also the grid parameters, which is the resistance, inductance, or all of these characteristics of them. And what we suggest in the other side is the model-less approach that only needs the measurement data. So we don't want to use any grid model information. What is the advantage and disadvantage? So the advantage of the usual analysis of the grid is that we understand what is the behavior of the grid and what are the capabilities. But the challenges there are the inaccurate and up-to-date model for this grid is not always available. So there are a lot of changes happening in distribution grids in a continuous way. So it's always difficult to capture all these changes and keep all the databases up to date, at least with the existing technologies. And there is always not always, sometimes differences between what the measurement says and what the simulation says. So that's why we say, if we use this measurement data and directly use them to understand the behavior of the grid, it can provide a valuable information. So it will help us to avoid all the effort and the effort that is needed to set up the link between the measurements and the model, so we can immediately have a plug-and-play applications, collect the data and build information based on this data to say what is the available hosting capacity in this grid, what is the how much additional electrical vehicle or how much additional PV can be added into this branch, whether this branch can manage it or not. So, and all of this will be based on something just based on the data, measurement data. And to give you a bit more of how it works, so this model-less approach is actually tries to estimate some of the important characteristics and behaviors of distribution grids, which are the connectivity between the nodes. So as soon as we have multiple measurement points, we can understand what is the connectivity between the nodes and what are the parameters of the assets of the grid just based on the measurement data. And coming back to our analogy between a tree and the distribution grid, so when we estimate the strength of the branch, in fact, this is we can estimate the strength of the branch just by the use of the measurement data, rather than taking samples of this tree. So this tree is moving up and down. So with collecting this measurement data, we can understand how strong is this tree. And we can also understand the connectivity between nodes of the tree by looking at how this tree is moving up and down with the external forces that are hitting there, instead of starting from one point and looking at the branches one after the other one. And all in all, it will help us at the end to understand how much additional PV and EV I can add into this branch, and this branch can sustain up to how much of the new loads or production. So with that, my presentation is done. This is one of the applications, one of the analytics that we are building based on this measurement data, DEPsys. And of course, I just have a take-home message for everybody. There are a lot of interesting mathematical tools that we can use and build many analytics. An important factor is always to keep in mind that there are physics there. So if you start understanding a little bit of physics or interpretation, our analytics will be much more accurate and usable. Thank you very much.